Hi folks. As you already know that there are three paradigms of machine learning, which are supervised learning, unsupervised learning, and reinforcement learning. So supervised learning, as again you know from another video, that it is about learning the functional relationship between the input and the output. So you have some kind of a training data set which has a set of inputs which are mapped to a set of outputs, and the job of your supervised learning algorithm is to learn the functional relationship between the input and the output. So one could say that this is a kind of curve fitting, and yes, it is indeed a kind of curve fitting, but with a very important difference. So supervised machine learning, as again I mentioned in an earlier video, that it is a kind of curve fitting, but without explicit knowledge of the curve. So here the crucial word is without explicit knowledge of the curve. So in usual curve fitting algorithms where we do curve fitting with a linear, quadratic, or an exponential function, we exactly know what we are fitting the data with. But when it comes to supervised machine learning algorithms, we generally do not know. But here, there is one important thing to understand is that this lack of knowledge is actually not a binary yes or no kind of a thing, but more of a grayscale. What does that mean? That means that in some simple versions of machine learning algorithms, we actually know the curve that we are fitting our data to. And so some of these algorithms, may be called machine learning, may not be called machine learning. There can be some, debate about it. But as we go to more advanced algorithms of machine learning, our knowledge of the explicit curve that we are fitting goes down quite rapidly. And as we approach the more complex models that are in use now, some of the deep learning models, there we almost have no idea about what the curve looks like. Now, of course, you may ask, okay, after all, we are using a computer algorithm where everything is written down explicitly. The computer is not really thinking on its own. It is just doing what the programmer has asked it to do. So in some sense, we do know what all the steps are, but the sheer complexity of the program is so much that we do not really fully understand what is it that the algorithm is doing. So as I said, there is a whole gradation of our knowledge, or you can say ignorance, of what the curve is that the algorithm is trying to fit the data to. So at the lower end of the spectrum, where we actually know perfectly what the curve is what is called linear regression. So regression is another word for curve fitting. Okay, so linear regression is a model where you try to fit your data to a simple straight line. So we are going to see the algorithm in future videos, but for now, let's just remember that linear regression is the simplest form of curve fitting. Regression is like curve fitting, and linear meaning that we are trying to fit the data to a simple straight line. So this is where we are in the very simplest stage of machine learning, and whether this should even be called machine learning or not, one can argue about it. Now as we move on from linear regression, we come to what are called linear models of classification. So notice we have come from regression to classification. The linearity still remains. We are still in a linear regime in some sense, but from regression we have come to classification. So regression was like curve fitting. Classification is also kind of curve fitting, but the objective of classification is to predict which class a particular data will lie in. So the naive Bayes algorithm that we saw is kind of classification, because we were classifying our email into normal or spam email. So here again there are many different algorithms, but for this course what we are going to study are logistic regression and linear SVM. So although logistic regression has the word regression over there, but it is basically a classification algorithm. And SVM stands for support vector machines. They are again a very powerful set of algorithms for doing classification, which again we are going to see in the course. Moving on from linear models of classification, what we have obviously are nonlinear models of classification. And there we sort of begin with SVM with kernels. What a kernel is, again, we will see later on. Don't worry about it right now. There are decision trees. And then there are these thing called random forest. So this is like the first set of algorithms that come under this broad category of nonlinear models of classification. Now as we move away from here again, so we are of course in the nonlinear regime, so we will stay there. Nonlinear is nonlinear, but what is more complicated than SVMs and decision trees are what are called these artificial neural networks. So they are again currently, I would say, the most advanced way of implementing machine learning algorithms. We will see a lot of details, but basically they try to mimic the human brain. So not exactly, they are still very, very different, strictly speaking, from how the human brain works, but they were an attempt to model how the neurons actually work. So that is how it started. Later on, people realized that it's not really a good idea to stick with the brain, and they moved on to more core computer science algorithms, but they are still called neural networks because the motivation came from modeling of the human brain. And so that was a major breakthrough in machine learning. And now this concept of ANN has become much more advanced and what is called deep learning. So deep learning is also usually implemented using artificial neural networks, but with a very special kind of a architecture, which we are going to briefly touch upon in this course. So this is kind of a very broad overview of the kinds of algorithms that people use in supervised machine learning. So now what changes as you go from linear regression to deep learning? What changes is, of course, as we know that we no longer exactly know what the curve is that these ANNs or even SVMs and the deep learning algorithm is trying to implement, whereas in linear regression or even in logistic regression and linear SVM, we exactly know the curve that the algorithm is trying to fit our data to. But one more very important thing that changes as you go from linear regression to deep learning is that here you have only one particular curve or function that you are trying to fit your data to. But these ANN and deep learning algorithms, they encompass a very broad family of functions. And as you change the parameters of ANN and deep learning in your machine learning process, you actually scan a very broad range of functions. And that is what gives ANNs and deep learning the power that they have. Okay, so linear regression, logistic regression, linear SVM, they all have a specific curve that they try to fit the data to. But ANNs and deep learning, they encompass a very broad family of functions. How that happens, we will again see in a later video. But for now, what is important for you to remember is this important gradation that exists in the supervised learning algorithms. So when we say learning, as you know very well by now, that it mainly comprises of two steps. So machine learning is equal to training plus testing. So what is training? So you have some data that is labeled. So you have some set of inputs, you have some set of outputs, and you try to find the functional relationship between the input and the output. And that is what your training is. Testing is once you have learned that functional relationship, you then apply it to the set of inputs in the test data and see whether your prediction matches with the corresponding outputs or not. And from there you can calculate the testing accuracy. Similarly, you could also calculate the training accuracy. So what is training accuracy? You use the training data to train your machine learning algorithm, and once that is done, you apply the algorithm on the same training data. Although the algorithm has been trained on the training data, but when you apply it again, you will not get 100% accuracy. Okay, so the training accuracy is a measure of how well your algorithm is able to predict the training data outputs, and testing accuracy is a measure of how well your trained algorithm is able to predict the testing data outputs. So now what you can do is that you can form a matrix. So what would this matrix contain? So here, let's say we have testing accuracy, and that can be high or low. Similarly, we can have training accuracy, and that can also be high or low. So now, if our training accuracy is high and testing accuracy is high, that is the ideal situation to be in. So this is where we have an ideal good fit. Now it may so happen that your training accuracy is high, but your testing accuracy is low. So then you would be in this quadrant where your training accuracy is high, but your testing accuracy is low. And in that case, we will say that the model has undergone overfitting. Meaning you have fit very, very well to the training data, but you are not able to generalize to the testing data. So this is a case of very high variance in your learning process. It may also happen that your training accuracy is low and your testing accuracy is also low. So in that case, you would be in this quadrant, and here you would be said to be in the regime of underfitting, meaning that you did not fit well to the training data itself, and so you are very likely to have a bad fitting to the testing data also. So this is a case of very high bias in your learning process. Now of course it may also happen in very rare cases that your training accuracy is low but your testing accuracy is very, very high, and that would be simply a case of fluke. what is called luck in life. Sometimes you did not prepare well for exams but still ended up getting very high marks. That happens only once in a while. So, if it happens to you once, don't think that, you are going to be lucky always. As they say, that the wheel of fortune keeps turning. Today you are lucky, tomorrow somebody else may be lucky. So, don't depend on that. Try to be in the regime of ideal good fit, where your training accuracy is high and your testing accuracy is also high. How to take care of overfitting and underfitting, we are going to see in future videos, because it depends on the actual model that we are trying to use. But basically the way to take care of overfitting is to either reduce the complexity of your model or use what is called regularization. Okay, so this regularization is a extremely important concept in machine learning, which we are going to learn in future videos, because the methods of regularization are different for different methods. Underfitting is usually a much easier problem to handle. You just increase the model complexity and that will take care of underfitting. So now we will see some of these complex models of supervised learning in future videos. But in this video, let me just tell you about a very simple supervised learning algorithm, which is called the Nearest Neighbour algorithm, or what is called the KNN. There is also a similar sounding algorithm called the K-means algorithm. So please don't confuse with K-means, because K-means is an unsupervised learning algorithm, while KNN is a supervised learning algorithm. So here, what do you do? So let's say you have some features, let's say 2 features for the sake of simplicity. You have x1 and you have x2, and you have some data points, let's say. So you have some data points of one class which are located like this, and you have, let's say, some other data points of some other class C2 which are located over here. And now what you get is a new data point, let's say, which is located over here. And now you are expected to find out whether this data points belongs to this class of blue points or to this class of red points. Now, of course, for us visually, it is very easy. We can straightforwardly say that, okay, this belongs to the class of blue points. But how will you write an algorithm to figure out the same thing? Or if you think for a moment, how did you figure out or decide that this belongs to the class of blue points? So what did you do? You kind of estimated the distance of this new point from all the other points in the blue category and also from all the points in the red category. That is what your brain did, even though you may not be fully aware of it. And what you noticed, even though you do not consciously know the exact values of these distances, but what you can very easily visually notice, that the distance of this new point from the blue points is smaller than its distance from the red points. And so you classified it to be in this category. And that is what the KNN, or the K nearest neighbor algorithm, also does. That it measures the distance of this point from all the other points, and then based on which category it is closer to, it classifies the new point in that particular category. So this is very simple to implement in Python. You can either use some available libraries or you can write your own code. The links to some of these Python programming examples are there in the description box below. So please do check it out and do code it in Python and see how this works. So now this example that we took of the KNN algorithm had only 2 features, x1 and x2. But what if there were many more features in our feature set? Would that cause a problem? Or, number of features, it doesn't really matter and we could go to any number of features as we want. As it turns out, As the number of features becomes important, the classification problem becomes that much more complicated, and that is what is called the curse of dimensionality. So curse of dimensionality was discovered sometime in the late 1950s, and what mathematicians and statisticians found is that as the number of dimensions or the number of features in your problem grow, the classification becomes that much more harder, because learning the features which help you in doing the classification become that much more complicated. So to see why that is the case, let us take a simple example and let us do some simple calculations. So like before, let us say that you again had a two-dimensional feature surface, meaning you have two features. This is your x1 and this is your x2. And let's say that this square over here represents your entire data set. So this is 0, this is 1, and this is 1. So the area of this square is equal to 1. So now let's say you want to do training of your supervised learning algorithm with a fraction f of the data. So then you will have to draw another smaller square, and this will basically be representing your training data. So now let's say, for the sake of simplicity, that your f is equal to 0.01, which means that you want to take 1% of the data and do training on that. So now this is a square, so this size, let us denote the side of this training data square as ed, which is a function of f. So this d, capital D, represents the dimensionality of your feature space, and this f denotes the fraction of the data set that you want to use. So now if your dimension is 2, meaning your E2 as a fraction of 0.01, what will that be? That will just be square root of 0.01, which is equal to 0.1. Now let's go to higher dimensions. Let's see what happens in dimension 3. So E3 of 0.01, if you do the calculation, it will again be nothing but 0.01 to the power of 1 by 3, which is equal to 0.215. So as you see, when we went from dimension 2 to dimension 3, the size of our cube increased from 0.1 to 0.215. And now let us increase it even further. When we go to, let's say, E100 of 0.01, what you will get is that this is approximately 0.96, which is almost close to 1. So as you can see that as you increase the dimensionality of your feature space, meaning that you have more and more features to worry about, then the size of this box that you're taking becomes larger and larger. So although the effective volume of the training data box remains 1%, but the size along any feature, any one feature, becomes very, very large, almost close to the entire range of values. And so what happens is that unless you have a very large number of data points in your training data set, it becomes very, very difficult for you to train your algorithm when the feature size is very, very large. So this is the problem of curse of dimensionality. There are some ways of handling it, which we will not be able to get into for the time being, But maybe in future videos we will try to touch upon some of these issues. But very interestingly, over the last couple of decades, I would say, there is a term called blessing of dimensionality, which some people have coined. So that is opposed to the curse of dimensionality, and some people talk of blessing of dimensionality. So what some mathematicians have shown over the last 20 years is that if the feature size, the feature space that you have is of very high dimensions, then the data can have interesting geometrical patterns. Okay, so in high dimensions, the data can have interesting geometrical patterns which can be exploited for supervised machine learning. So this is still an ongoing area of work, and we don't exactly know whether this applies to all kinds of database. Certainly not. It applies only to specific kinds of data sets. But the good thing is that there are at least some kind of data sets where dimensionality can be a blessing instead of being a curse. One simple example is when your data has very little noise. So one of the reasons why dimensionality becomes a curse is because usual data sets have a lot of noise in them. But if your data set has very little noise and has very high signal, so the signal to noise ratio is very high, even then dimensionality can sometimes be a boon or a blessing instead of being a curse. So in this video we discussed some issues and some aspects of supervised machine learning. In the future videos we are again going to take this topic further and learn specific algorithms and more details of how supervised learning is actually done in practice. Till then, stay connected.